Yeah.
Okay, so welcome everyone to today's Pore Lab lecture. We're very happy to have Ron Holtzman here today from Coventry University. Ron has received his PhD from UC Berkeley, working with Tad Patzek on micromechanics of granular materials. He was also a postdoc associate at MIT with Ruben Juanes, studying multiphasic flows in deformable porous media. And he's now an associate professor at Coventry University. He's also the leader of the engineering applications of fluid mechanics group there. He seeks fundamental understanding of environmental and energy applications in which multiphasic and reactive surface flows are key. So I think there are lots of common interests between his research activity and the things that we like to do here in Pore Lab. So I'm sure many of you will benefit from his talk. Okay, Ron, so the floor is yours.
Okay, thank you, and thank you for this invitation. It's great to be in Oslo again.
Yes.
And this work is done together with my close collaborators and friends in Barcelona, where I've been before Coventry, which I really miss. So Marco Dens in IDEA, CSIC, and Ramon Planet, which you know well, and Jordi Ortin from University of Barcelona, the Institute of Complex Systems. So what I will do today is I will present a very kind of simple, elegant model that allows us to link the pore-scale mechanisms behind the macroscopic wetting, dewetting, or drainage-imbibition hysteresis, and also do some energy balance to show the energy dissipated in these cycles. And the nice thing about the model that allows us to do that is that it's a really first principle model using only physical, non-adjustable parameters, which, as I will show, kind of avoids some of the pitfalls that the state-of-the-art models, specifically the compartment models, so-called, stumble into. And most of it is quite new. We published some of it a few months ago, so I'm kind of curious to get your input. So let me start. Yep. So I won't bore you with Greek. My daughters are now studying Greek because of Percy Jackson, but I will not try my luck because last time I did some mistakes. So anyway, hysteresis, we mean, or path dependence means that you apply an external forcing, and the response to this forcing depends on the history, on how you apply it. Like, if you start bending a stick, so it's not how much you bend or what force you apply, but it has to do with the history, how many times, or if you do it fast or slow. And it's common to many physical systems. In particular, our interest is in quasistatic or slowly driven systems. So one, probably the most kind of well-studied in stat phys is ferromagnets. So you apply an external magnetic field, and you have different kind of magnetization depending on the path. So you can have, if you increase or decrease, you have a different magnetization, and you can also do these partial loops. So you can do an inner loop or secondary loop and a tertiary loop. And what you also found, another kind of common feature, is this return point memory. The fact that when you do an excursion, you return to the previous curve, and also in this smaller loop, at exactly the same point and with the same kind of microscopic configuration. Okay, so this will become very important in a few minutes. And this is evident in many systems, also in memory alloys. This is heating and cooling a memory alloy, so the stress-strain behavior of this one. But today I'm going to talk about wetting, dewetting, or drainage and imbibition in fluids. So specifically, we're looking at the capillary pressure saturation response. And we can see that, for example, if we start with a wet porous medium, when we drain, we get one path, one set of saturations for a given pressure, and then we get a different ones, or for example, for the same saturation, we have a lower capillary pressure in imbibition. So they don't follow the same path. And also, again, you have this return point memory if you do partial cycles. So you have this multivaluedness. Okay. And this has, of course, as you know all very well, important consequences for many, many applications, because in many applications we do have this kind of cyclic flow, and we see this appreciable hysteresis. In water resources, you have this wetting and drying cycles. In soils, in CO2 sequestration, for example, after you stop the injection, after you push the brine with CO2, then you'll have imbibition back to some extent. In many, many kind of applications where you push the contaminants, oil, water, hot water, and then you stop the injection, so then you'll have some kind of rebound. So also enhanced recovery, contamination, remediation, and also a different kind of industrial applications like microfluidics or fluid cells. And this is also important not just to understand the physics, but also because the pressure saturation relationship, this kind of so-called retention curve, is a major constituent in the classical multi-phase flow models. Like Richard's equation, it's used as a constitutive relation. So we really want to pinpoint to have a good model for this. So we understand the source for hysteresis quite well, qualitatively, or not qualitatively, sorry, quantitatively, but more on the phenomenological level. So we know that the underlying source goes back to the Haines ink bottle effect. And just to make sure that we are all on the same page, so I will use drainage for pushing the wetting fluid with the non-wetting fluid, and imbibition for pushing a wetting fluid which pushes the non-wetting fluid. Okay, so if we have this ink bottle effect, or this convergent divergent pore structure, which is common to all porous medium, essentially, they are not a pipe, with a fixed radius. So if you're here in drainage, so pushing, this is the non-wetting and the wetting. If you are at where it starts to constrict, where the radius starts to decrease, then you have to keep pushing, you have to keep increasing the capillary pressure to go to this narrower portion. And this is completely reversible. So you are here on this pressure saturation, kind of the energy landscape that is formed by this quench disorder, the heterogeneity, and you are simply climbing steadily on this one. You have to keep increasing the capillary pressure to increasing the curvature to push yourself inside. And the same with imbibition. If you are going into a wider spot, you are here and you have to keep decreasing, and this is reversible or stable. Okay, but what happens when you are in drainage, for example, at a constriction, where now it becomes wider, then suddenly the interface becomes unstable and jumps to a next equilibrium configuration. This is a metastable advancement from here to here, because this is the energy landscape. So you have this local well. So once you're here at the same capillary pressure, you jump exactly here, and the saturation will change without changing the external force. So we know all that again for quite a while. And we have models that can capture and reconstruct the pressure saturation hysteresis very nicely. And the most popular models are what we call the compartment models. In fluids, it's the Leverett model. In magnetic systems, it's the Pryzak model. And what they are built of is this concept of, again, the ink bottle, if you want, but what they call hysterons, or hysteretic units. So each unit, and they are independent. So each unit has this kind of energy landscape. So you can think of that as a bunch of pores with some sizes. And then you tune the statistical distribution of these units, for example, the number of large pores and small pores, to get, and the behavior is just the sum of them. So that's why I'm saying they don't interact really. They are just kind of independent. So just the sum of the response, and you can tune it to get the exact pressure saturation hysteresis that you want. The problem is that the energy kind of functional, this energy landscape is really heuristic or phenomenological. And this is not just because you tune it, because, well, you tune the energy landscape because you don't have another choice, because these hysterons will be invaded for fluids once the macroscopic forcing will exceed the total, the local threshold. So this respects the allowability if you wish, thermodynamic allowability. So once you have the capillary pressure large enough to invade these large pores, all the large pores in drainage will be invaded, regardless where the interface is, even if you're still here. And this, of course, ignores accessibility or the spatial location of the interface versus the pores. And this is okay for magnets, but it violates mass balance in fluids. And there is another kind of approach that started a while ago by Hassanizadeh and Gray, and this is what I call the math approach, where they show that you can recover hysteresis by essentially adding more parameters. So they say it results from incomplete parameterization, where they add different topological parameters like the interfacial area, Minkowski functional. This is more recent papers, and they do show nicely that it eliminates or recovers this hysteresis. However, and this is quoting, I think the paper by Miller, determining all these parameters is an immense challenge, imaginative, as they said, experimental and computational challenge. So what we offer is a simple model, which is based on the simple conceptual model that can be realized experimentally and analytically very easy. So this is a Hele-Shaw cell with a perturbation. Essentially, it has a change in the thickness locally. So we do quasistatic displacement. This is the cell, this is a perturbation here. Okay, so zooming in, you have like a change, a local change in the aperture, like a rough fracture. And then we change the height of an oil reservoir to push, we increase it to push oil in. The height is capital H, and we decrease it to push it out in small increments, and then we wait for equilibrium. So it's a quasistatic, and when we decrease it, then air invades from the other side. And we tilt the cell slightly upwards, so imbibition goes against gravity to avoid fingering. Okay, let's start with a single defect, just one of these patches, and this is manufactured experimentally with a copper patches that are put in a glass cell. And the single defect really provides a lot of insights. Later we'll introduce a disorder, which is the interesting part. And this is again really doing our homework. We read the Jens papers, of course. This is from his work on this is on the contact line hysteresis. And he remarked that this single defect really essentially filtering away some of the complexity which arises from the interactions between multiple defects. So the statistical complexity, you can filter it out and understand better. But as I will show, there is a caveat here, because using only one defect, eliminating all the interactions can be a little bit misleading. So this is an experiment. This gray area is the defect. You see that we touch it, we deform in a jump, then we slowly undeform it or make it straight. Then we deform it in drainage again and experience another jump at the other end. And this is for a protruding defect, a decrease in the width. So there's an irreversible jump here. You can see this is let me play it again. So this is the deformation, so zero deformation, a jump, then a constant, a rigid body motion, and then this flattening. And then in drainage, you reverse the path, so this is completely reversible, and then the jump occurs at a different distance or a different saturation. Okay, so you have here a reversible, so this is the pressure saturation or the height saturation. So you have a jump, this is imbibition in blue, a jump, then the reversible part, you deform it, go as a rigid body, and then you straighten it in a jump which occurs at a different saturation or height. So this is the irreversible or the dissipated part. So what we do to model that is, again, a very simple kind of setup, or just solving the equilibrium configuration by solving the pressure balance on the interface. So in interfacial configuration is the height at each point x. X is the lateral axis. So y is the kind of along the cell. So h is the height of the interface from the origin. So we solve at every point this equation, this equilibrium equation of pressures. So the first term is the interfacial tension. And this is for a given external forcing P. P is just rho G capital H. H is the reservoir, the oil reservoir. So for external forcing, we solve for H. So the first term is the interfacial tension, the in-plane curvature. This is the interfacial tension term. So the second derivative. The second term is the gravity. So this is GE is the effective gravity. So it's G times the sine of alpha, the tilt. Then the external forcing. So this will be a restoring force, or this is a stabilizing force. And then the distorting force is this term, PC, which is the change in capillary force. This is the out of plane curvature. So as you go, as the interface comes here, touches the defect, it experiences a change in capillary pressure, and this pulls the interface in imbibition, for example, if it's a protruding defect, pulls the interface and deforms it like that. Okay, so B is B0, the cell, the Hele-Shaw cell kind of mean width, or the external width, and then you have this delta B, the change. So B is just the sum of those. So B is changing. And this is the expression, the change in capillary pressure due to the out of plane change in thickness. Okay, and obviously you would note that there's a missing term here, the viscosity or the velocity, and this is because we are considering a slowly driven system, a quasi-static, but as you know all very well, even in slowly driven system, you have the jumps are very rapid, the velocity magnitude is can be orders of magnitude faster than the mean displacement that you drive the interface. So you have these jumps, very rapid jumps, as you saw, and this will be important in a few minutes. But for now, we are thinking of quasi-static, no viscous effect. We're thinking of solving the equilibrium configuration, so starting from one configuration, changing P, changing the external reservoir height, and then solving for the next equilibrium static configuration. And this is equivalent to energy minimization, so we can write the Hamiltonian for this system, again, these four terms, and then take the derivative, find the minima by finding the zero, the local minima of this Hamiltonian. So again, the beauty of this model that all these parameters have clear physical meaning, namely that you can go and measure the interfacial tension, the effective gravity, all of them have clear physical meaning. You can measure them in the lab, surface tension, the pore geometry, and you can design and control it very accurately, experimentally. And this allows us to do this experimental validation, and also for the single defect, at least we can do an analytical kind of validation. We can solve the Hamiltonian. So this is what I will show you now. But before, just on the implementation, so it also allows us for a very efficient numerical implementation. What we do is synchronous updating. So this is akin to what is done for the random field Ising model, the zero temperature or fluctuationless random field Ising model for ferromagnets, where essentially at each step, so after we perturb, after we change the pressure, starting from equilibrium, external pressure, we write this equilibrium equation for each x, for each point along the interface, these four terms. And then we find all the points which are out of equilibrium, which for imbibition is when this PE is larger than zero. For drainage, it's the opposite, when it's less than zero, which means that you're not in equilibrium, the interface wants to be pulled up, and this will start from this term, which will be positive if it's protruding. So the interface is sucked up. So what you do to find the equilibrium configuration is just increment in small increments iteratively, simultaneously. So we don't care where these points are. All the x's where we find that P is PE is greater than zero, we increment them and then return, find if they are in equilibrium, and we repeat this cycle until we get all the points to be close, approaching to zero. Okay, and the same, but for less than zero for drainage. And surprisingly, this very simple algorithm provides you with the right behavior, with exactly the right behavior and values. So again, this is a simulation of the single defect. So you get this rapid jump at the entrance in imbibition and at the exit, but again, a different location giving rise to this hysteretic cycle, which again doesn't involve disorder yet, no heterogeneity, just a single defect. Okay, and now we can compare the experiments to the simulations to the analytical. So the analytical is just, of course, make sure that the theoretical analytical expression by solving the Hamiltonian, just to make sure that we converge accurately to the right solution. And this is indeed met. So the numerical is filled dots, and the line is the analytical. And also the match to the experiment is surprisingly good, given that there is some uncertainty. And this is due to the alignment of the cell, the fact that we don't really reach pure static equilibrium. And also because of image analysis, the interface has a 3D curvature, so it's hard to say exactly where. It's not a sharp interface visually in the 3D, and then it's hard to say where exactly the interface. So we have some uncertainty. Okay, so this is very useful. And we also checked analytically versus many other types. So we have many experiments, but we can also, of course, play very easily with analytically, and there's perfect match for various gap spacing. So this B0, the defect width W, and the angle of the effective gravity. So exact match up to the numerical accuracy with the simulations. Okay, now I want to do a detour before we go to the disordered medium and look at what we called a weak defect. So what I showed so far, this mesa-defect is a strong defect. And a weak defect is a term coined by Dejean a while ago, that he made the distinction saying that a weak defect is one that the interface remains in equilibrium while it advances along it. And this can be achieved by varying this term, this out of equilibrium curvature, capillary pressure term, in y, in the direction of advancement. Okay, so for example, here we do it linearly. We have like a linear change and then some plateau. And this means that as you touch the defect, you actually see larger and larger kind of pulling until you get to the plateau. And if you design it correctly, not too strong, if the slope is not too strong relative to the elasticity of the interface, then you get a weak defect. And the way that this deforms looks like that in the simulation. So you see there's this growing deformation, but it's completely reversible, as you would see. Now we get to the edge, we are pinned, we go back in drainage in red, and you can see, of course, this is reversible also for the strong defect, but now you will see that even this part, leaving the defect, is completely reversible. And as I will show, there's also no dissipation, no energy dissipation, and we can compute that, as I will show in a minute. Okay, so it's the substantial deformation, but since it's a weak defect, then there's no dissipation or hysteresis. Now we can take two of these defects and put them far enough together, and as you would expect, this remains weak. So this combination remains weak, so that the advancement in imbibition and drainage are completely reversible, including the exit in drainage or the entry in imbibition. So now you will again undeform and live quietly without dissipating any energy. And this is not surprising. This is actually conforming with the view of compartment model, where hysterons are by definition are strong. So if they are weak, if they're not hysteretic, the units, so you have no dissipation and no hysteresis. But if you bring them close enough together, then you get this dissipative jump, which is non-reversible. The jump in imbibition is different. It's a little bit hard to see here, but there is a small hysteretic cycle. So the overall, the macroscopic response of this pair, this weak pair, if they are sufficiently close or they interact, is strong. So you have hysteresis and dissipation emerging, even though each of these units is not hysteretic, and again, it's not a hysteron. Okay, so this contrasts. So you have a dissipation cycle here, or a dissipative hysteretic cycle, and this is contrast with what you would expect from a compartment model. Okay, and if you bring them even closer, you get a stronger jump and a larger hysteretic loop. And I didn't show you yet, I will show you in a minute, how I compute the energy. But if I compute the energy dissipation, so this is the three cases that I showed you. So you can see and this is the distance between the defects normalized by the capillary length. Okay, this is interfacial tension, the effective gravity, and the density. So this is the Jurin height. So this is the distance, the normalized distance, and this is the total dissipation along this psi total is the total dissipation along this cycle in imbibition and drainage, the cumulative dissipation. So it's zero if they are far enough apart, but at some distance they start interacting, and then you get some dissipation, and this dissipation grows as you decrease the distance. And we are now working on predicting theoretically the onset. This is still in progress. Okay, so I owe you the explanation for the energy balance, but first I want to show some of the results for the disordered medium. And the disordered medium, as you would expect, is just realized with a bunch of these copper defects experimentally. So we populate them randomly or by imposing some distribution, and we get this random cell spacing. We can impose the thickness, for example, a Gaussian or a dichotomic, just zeros and ones. And this is a nice proxy for a rough fracture or a quasi 2D porous medium. So this is an SEM image showing these copper patches, okay, and a schematic. So this, of course, makes it much more interesting, because now it's much more rich behavior. You essentially have interactions between the defect, of course. So you have these collective or non-local interactions. You have a very strong defect. When you have a very strong defect here, it pulls the interface and it affects what happens in the entire cell. Because of interfacial tension, you get these very large avalanches. So you get all this because of successive jumps. And again, this is something that we want to explore numerically in the simulations. And the exact same simple model that I showed you before, just solving independently or doing this synchronous update in all the out of equilibrium point at every step, solving this equation iteratively does the trick. It very accurately finds at every reservoir pressure, or every reservoir height, it finds the interface configuration age, and you see it captures these very non-local interactions, these large deformations. Sorry. Yep. So you get these non-local deformations. So each of these, let me stop it for a second. So each of these pixels is a 4x4, each of these dots is a 4x4 kind of element, a defect. The strength is shown as the color bar. So this is a Gaussian distribution centered around 0. So this is strong protruding, this is strong intruding or negative defect. And you can see that you get this suction by the strong defects, positive defect in imbibition. Okay, and then as you go to drainage, you get the spinning and depinning based, again, these non-local interactions. And we also can investigate the returned point memory property. So you see we do this inner loop. So you get from this very simple stepwise linear model, all this complex behavior, the avalanches and everything. Okay, so we get this complex nonlinear response, hysteresis, obviously, multivaluedness, so this is imbibition and drainage. So at a given pressure, we can get 4 different configurations and saturations, 2 for the outer loops and 2 for the inner loop. And if I continue to make more loops, I can have infinite amount of configurations and saturations. We get this large deformation, the avalanches or the intermittency, and the cooperative effect of interfacial tension. And we can also get, and we got it exactly, the returned point memory property, where at this point, we don't just recover exactly the same pressure and saturation when we close the cycle, but we also recover exactly the same interface. So the interfaces overlap exactly. And this will be important for the energy. And this allows us to explore different aspects of the system. For example, what is the effect of the heterogeneity, the microstructural heterogeneity, how you populate these patches. for example, these different degrees of disorder. So this is for this Gaussian distribution. This is a wider Gaussian. This is the standard deviation. And this is a narrower Gaussian. So you see that the pressure separation curves get wider and wider with the distribution, okay, because you have stronger defects. You have statistically a much stronger defects that affect the entire behavior. And this is, by the way, smooth by doing this ensemble average. So each of those is 100 simulations. And I only show here the ensemble average to get rid of the details of specific realizations. So the larger the standard deviation here of the distribution, the larger the hysteresis cycle, the more hysteretic it is. And you can quantify that, for example, measuring the width of the hysteresis cycle, this delta P. So the black circles here are the Gaussian distribution. And you can see that they fall nicely in a log-log plot on a straight line. So you have this exponent, this power law behavior with an exponent that surprisingly is identical or very similar to a wide range of distributions of defects. You know? So we get this Gaussian, again, for different standard deviations. So this is between a positive and negative Gaussian distribution. We can get a positive Gaussian, so just truncating just the positive side. Again, this will be these open circles. You can get dichotomic, so just between a value and zero. So all of them are at this maximum value. So you only have zero and this value. And you can have, all of those are at 35% occupancy, coverage of the cell of defects. But you can also reduce the occupancy. So go to 17%, 8%, 4%, 2%. This is 2%. And also go to ordered medium, where I place them again. This is the Gaussian, where I place them order. And you see that for various distributions, this scaling holds. And I admit that we still don't have an answer, a quantitative explanation for that. But I think it is an interesting observation showing this nonlinear dependence resulting from the interactions of the defects because of the lateral correlation that arises from the interfacial tension. And the fact that even at a very small density, was somewhat surprising for me, for this dichotomic, you still have the same scaling is because the correlation length, LG, is much larger, even for this very small, even for this one, it's still much larger than the distance between the defects. So the correlation length is about, I think here it's about 10 millimeters, and the distance between the defects is the order of I think 0.1 or even less millimeters. Okay, so you always have the defect close enough so they interact strong. We can also play with the effect of gravity, or the bond number, so changing the tilt of the cell. And as you would expect, as you decrease the bond number, so going here, tilting less and less the cell, this is almost horizontal, you get much larger avalanches because gravity opposes the jumps, and much flatter pressure saturation because these jumps saturations are much stronger. With every small change of pressure, you sweep almost the entire cell. And this is typical to retention experiments like the one, Marcel, that you did experimentally. Or the typical kind of way that in soil physics, they do the experimental retention curves. So I'll return to gravity in a moment. But what I want to do is now go back to the energy balance. We still have about 10 minutes, right?
Yes, feel free. We have more 10 minutes, but we're a bit flexible, so okay. Don't worry.
So I want to go now to the energy balance. So simply what I write without the effect of viscosity, that the external work will be idly stored, part of it, so this is W, will be either stored, and D is the differential or the change between two equilibrium configurations. So U is the internal energy, or dissipated by acoustic emissions by elastic waves. So this is psi, okay? And I take the convention of, I write it here as negative, as dissipation, but in the plots, I'll just use the positive. So how do we establish those? And this D bar is for non-state variables. So U, as I will show, is a state variable. These are non-state variables, of course, in the thermodynamic sense. So how do I establish U and W? Well, I split the Hamiltonian into two parts. I write it as U minus PSW. So P and SW is just the integral of H times dx times along the length, the lateral length. So if I do that, I get the following expression for U. So U has again the interfacial tension term, the out of plane, sorry, the in plane curvature, the out of plane curvature, and then the height of the interface, the gravity. And this allows us to compute analytically the stored energy. So the difference between two configurations at time 1 and time 2, or at P1 and P2 will be this differential. And W is just PSW, or the change in the work is PSW, PDSW, which is the pressure at that step, times just summing over or integrating under the interfacial area. Sorry, under the configuration under H. Okay, so that's just the area covered by the wetting fluid. Okay, and we also validate that analytically, but and as I will show, you can validate it for the total cycle. So this the internal work, we can show that this is a state function. Why is that? Because it only depends on h, on lowercase h, the interface height. And we already showed that because of the return point memory, that h always recovers its initial value in closed cycle. So even if you start a second branch, you will always get to the same exact equilibrium configuration, the same h. So what this means is if you would integrate over du, you would get 0, no? Because if it's a state function, you get exactly the same. So all the energy stored will be reversed. So the total energy dissipated, so integrating over deep psi, is just integral, just looking at this one. So this will be 0, the integral over that. And what you get is it's just minus PDSW, the integral over that, over the entire trajectory, which is nothing but the area enclosed inside the PS curve, inside the retention curve. And this will allow us to validate our calculations to compare the summation of this stepwise or summing the dissipation along the jumps with this simple calculation. So let's look at the simulations. So this is, again, the pressure saturation. This is the interface. And now I will also show the jumps in individual events. So this is the amount of dissipated at each step, from one step to the other. So this is this deep psi, or psi xt. And this is the integral of deep psi. This is the total cumulative dissipation along the entire cycle. Okay, so let me run it. So what you see is that every once in a while, of course, this kind of erratic displacement, these avalanches, and during these avalanches now in drainage, you can see the interface doesn't move, or it moves very slowly, and then you'll have a jump, you have the deep pinning, and this jump, you can see that in the colored events here, results in a very strong event. You can see that you suddenly have this very strong dissipative event, which leads to most of this cumulative behavior. Okay, so most of the dissipation occur in very few, very large avalanches. Note, this is many orders of magnitude. What you also note here is this very wide range of magnitudes, both the energy dissipated and the avalanches. Avalanches I call the amount of saturation change in the jump. So, for example, if I plot the PDF of the energy dissipated in each jump, so this deep psi, normalized by the amount of energy, the absolute value of the amount of work, during that is kind of performed or reversed back to the system during this jump. So what you see is that you have a very, very wide range of magnitudes. Okay, and so for example, this is for this simulation that I showed you. This is for the very wide distribution of defect strength, this red curve. So you can see 4 orders of magnitude. And what you also see is that this range will depend on the system properties. So if I decrease the standard deviation, so if I make weaker and weaker defect in my, here it's again the Gaussian, so I get still a big range, but at a much smaller values of dissipation. And another very interesting feature here is, if you look at the x-axis, is go beyond 1. So here, for this very strong kind of strong system, also very strong defects, you get that the dissipation in a step, in one the jump, one Haines jump between one static equilibrium configuration and the other, can exceed the work invested during this jump, to make this jump. And this should not be a surprise. It did surprise me for the beginning, but of course this should not come as a surprise, because the energy released in this step can be stored during many, elastically stored during many kind of jumps, or many previous configurations, many steps, and it released in one step. We can also plot the dissipation, the energy dissipated in a step, so the distribution of dissipation versus the distribution, this is the avalanche size, if you wish, the size of saturation change in each step. This is for the very weak system and the very strong system, or the very large standard deviation. And what's interesting here is that you see that they don't all fall for each case on the same, on a single line. So you naively, and I expected that so of course for large avalanche, for very strong delta S, you get very strong dissipation, but it's not exactly proportional. So some of them are larger, some of them are smaller. Again, this was also found by Joe Diotin for magnetic systems. Okay, so it surprised me, but it didn't surprise them. Now we can look at the total dissipation. I'll try to wrap up in a few minutes. So the total dissipation in a closed imbibition drainage cycle. So this is also, again, can be quantified by the area enclosed in the cycle. So this can this validates our computation, and it's actually accurate within a fraction of percents. This calculation of summing up over all the steps. And this can be important practically, estimating the total energy dissipated in a closed cycle, for example, for estimating the cost or the efficiency of different applications where you push and withdraw fluids. And of course, since, as I told you, the area in the PS cycle is exactly the amount of energy dissipated in the cycle. So of course, we recover the same scaling, which, as I said, we don't have an explanation yet. So this is exactly the same kind of 1.4 exponent. And looking at the effect of gravity, so this is small gravity or nearly horizontal, very large jumps in saturation. You can see almost half of the dissipation along the imbibition is in one step. And then in drainage, again, very strong events. And in nearly, or this is actually vertical. So now we increase gravity, we decrease the Durin heights. So now the jumps are very small, the avalanche sizes, and hence the dissipation. So you can see, you can hardly see that there is hysteresis. So there is a cycle, but the cycle is very narrow. So the total dissipation is much smaller than here. It's an order of magnitude smaller. And also the size of the events, you can see at a different scale, are much smaller. Okay, and looking at the total dissipation in the cycle, again, low gravity, nearly horizontal. And as you increase the gravity, as you tilt the cell, decreasing the Durin height, the amount of the jump that is allowed, you get smaller and smaller total dissipation, as you would expect. Okay, and the last result that I want to show is the comparison with experiments for the disordered medium. Okay, so this is for a dichotomic distribution, because this is what we can manufacture easily. And you can see that the response is quite different. So it's about 20% larger area. The blue is the experiments, these dots, and the line are just connecting the points where we measure the saturation. This is the pressure saturation. And the red is the simulations. So the area in the experiments is about 20% larger in the experiments. And why is that? This is because viscous dissipation, as you would expect, is important because of the jumps. So even though we are doing this quasi-statically, in a jump, the velocity can be a few orders of magnitude faster of the interface than the mean displacement velocity, which is very slow. And you have an additional term, if you wish, or additional dissipation mechanism that is not included in our model that I used to generate the red curve in the simulations. And this means that you'll have in the experiments excess dissipation requiring a larger amount of work, for example. So we have the imbibition, and now we try to drain the cell, we try to reverse the displacement. You will need to suck more, you have to increase the suction, to increase the capillary pressure or decrease age lower to apply a larger suction to get to the same kind of saturation. So for a given saturation, you have a larger suction. And here we do the experiment and the simulation under the same pressure. So starting here from 6.5 and ending at 5. Okay, so you get a different area, meaning that you have more energy dissipation in the experiments. And this is why you need this larger suction or to invest more work to get to the same saturation. But what you can also see that the change is not that dramatic, right? So it's about 20%. I mean, it is noticeable, but still I would argue that the interface elasticity is the dominant mechanism in quasi-static, of course, displacement. If you have larger and larger displacement velocities, then of course forget it. And also, so this really is a lower bound, okay, for an inviscid fluid. This would be the Euler limit of the Navier-Stokes equation. So it gives you a good approximation which provides a lower bound for an inviscid fluid. So to summarize, I showed you this simple model based on first principle, what we call the bare model or bare parameters. The parameters are not tunable. They have an exact kind of physical meaning. And this is a big improvement, I would say, from the state of the art, because it allows us to expose the role of the spatial distribution of the defect or the microstructure, the spatial effect, this emphasizing this difference between allowability, so the thermodynamics of did you get low enough in terms of suction to drain all the large pores, and accessibility. Are you in contact? Is the interface, did you reach that part of the sample to invade all the large pores? It also shows that the dissipation and hysteresis can emerge from cooperative behavior, this non-local cooperative behavior between objects that are intrinsically non-dissipative and non-hysteretic, so they are not hysterons in these compartment models. Okay, so, and this simple model provides, again, a nice kind of quantitative explanation or exposes quantitatively the link between the microscopic physics, allowing us to capture non-equilibrium, hysteresis, multivaluedness, and memory properties, linking this kind of small scale physics to the large scale, kind of to the cooperative Haines jumps, and then to the large scale hysteresis and associated energy dissipation, where again, we can estimate the dissipation. And we found that for quasi-static displacement, we get this lower bound, the nice approximation, not so bad because interface elasticity is dominant and not viscosity. And again, as I showed, the total dissipation in a cycle coincides with the area of the pressure saturation cycle. And this can be tuned by the system properties. I showed how I tune it with gravity or microstructure. It can also change, of course, interfacial tension and other properties. And we also showed that dissipation in a jump, in a jump between two equilibrium configuration, can vary by orders of magnitude, can be much larger than the work invested during this jump because of this elastic kind of memory, and does not have to be proportional to the size of the avalanche, again, as found for ferromagnets by Jody a while ago. So with that, I want to thank you for your attention and welcome any questions.
Super, thank you very much, Ran. Do we have any questions from the audience? Maybe I could start with one myself while people are thinking. So one thing that I find quite interesting from this model, and also like from when I heard it from Jordi and Marco and from you and conferences around, that you didn't make any explicit mention to the need of contact angle hysteresis to generate the drainage-imbibition loops, right? So in real systems, do contact angle hysteresis, do they add, like, is this like a parallel source of hysteresis, but not crucially necessary to explain the hysteresis?
Yeah, very good point. So the answer is yes, it will add. Not crucial in our system, yes, otherwise we wouldn't get this very nice agreement. But it could be crucial if you have very strong contact angle hysteresis. So here we use silicone oil, which is kind of perfectly wetting and air. But if we would use something else, or if we, of course, will drive the system much faster, and this is something we are constantly working on, or thinking now, not working yet, about how to introduce dynamics. So then if you do have a strong effect of contact angle, then yeah, this will sound being important, and we will have to introduce it. But yeah, for us, we don't have really a strong effect of the contact angle using the silicone oil.
Hi, I have a question. Can you hear me?
Yeah.
Carl Fredrik here from Trondheim. I have two questions, I think. The first was a couple of slides before you said that the difference between the simulation and the experiments were due to this, that you have, I didn't really get it, or was it because you had more dissipation during the jumps because of the high velocities?
Yes, exactly. So if you look at this point, now we get in the imbibition, now we reverse the displacement. So now we start pulling the interface back, and then you start having these dissipated jumps. So in the simulations, in the red, we have no dissipation. So we have no viscous dissipation. So the dissipation is only by, again, the deformation of the interface, and this is what we compute here. But in the experiments, actually, you get the same jump, so you get the same deformation, but because the jump happens in much faster velocities than you typically drive the system, you get extra source of dissipation. So you have really to invest more work to get it to the same saturation, to drain a specific portion of the cell or a specific area. And this is why you have a wider cycle, and you get to stronger suction. Again, to get to this drainage or to this drainage, you apply stronger suction, because we don't account for this energy that is lost in our energy balance or in our model.
But could some of the explanation here also be that you have this contact angle hysteresis? That you have other sources of hysteresis than what you're seeing in sort of seeing geometrically?
Yes, again, I think that if you do have strong contact angle hysteresis, and sometimes, of course, we do have, it was shown experimentally, no? So when you do have a strong contact angle hysteresis, it will add, and this will even increase further the agreement between our simulations, which doesn't account for that, and the experiments. But I think for our system, this is not so important because we use this very strong wetting silicone oil on the glass. So yeah, we are not yet clear. I mean, the next step that we're going to do now is to do this on a single defect very carefully and try really to pinpoint, is it really only viscosity or is it other things? But I think as long as you drive it relatively slowly, so contact angle hysteresis is not very important, and it's really perfectly wetting oil, I have a feeling that most of this in agreement is due to the viscosity in the jumps.
To follow up on that, if you're running your experiment in some sense even more quasistatic, sort of even slower, do you think you will have a better correspondence between your simulations and the experiment?
Yes, but up to a point. I think at some point you will have this kind of fluctuations that I'm not exactly sure the source of which, but they were shown experimentally that after a while you'll start getting this kind of sort of equivalent to thermal fluctuations, even though you don't have any thermal effect here. So I think it will improve slightly, and we didn't, definitely in this experiment that we show here in the blue, we didn't wait long enough. We just say, oh, it's almost static, and long enough would mean that Ramon will have to spend days in the lab because it never stops. Yeah. So yeah, this is definitely a source of error, but I'm not sure that we can minimize this error, and for sure, even at very slow displacement, we'll still have the viscous dissipation in the jumps, which is, again, becomes totally non-correlated to the velocities are totally non-correlated to the driving of the system at very slow velocity, and we will still have that. So we will never have a perfect. For that, we have to introduce viscosity rigorously into the model.
I think Knut Jørgen has a question.
Yes. Thanks a lot, Ran. It was a really, really interesting talk. And I have a question. How will the size of the jumps depend on your system size? And are you able to, predict that?
If the size of the jumps?
The size of the jumps. I guess you will have a cutoff for the size of the jumps that you have. That will depend maybe on the size of your system. I mean, when you get your system size bigger, your jumps will get bigger. And are you able to, predict that kind of cutoff for the jumps?
Yeah, it's a very good question, and of course, and we try that. So for very small system, you have actually crazy jumps. No? So we have a very strong pinning event, like a pinning site or a very small constriction. It will pull the entire interface in all the system. But once you have enough kind of width relative to the gravitational length, to the Jurin height, so the capillary length. Sorry. So once you have enough, you sampled enough statistically enough of the defects, then it doesn't really matter. And I did, for example, in this one, we tried different widths because this was very wide cell experimentally. So it took days and days, even though it's such a simple model to take all these loops. And I tried on much smaller systems, I think a third, and it gave, and then I did ensemble average, and it gave exactly the same results. I mean, not exactly within these perturbations, but the curves went one on top of the other. So I think as long as the system is not too small above the threshold, which depends on if you're sampling enough of the defects, and if you allow, again, the system to be large enough so the very strong defects, the very extreme, doesn't talk to each other that strongly, then yes, you are not dependent anymore on the system size.
But if you do this in more like a normal porous medium, not like a fracture like you have here where you have a gap, what you see is that the size of the jumps will depend on the size of your system. A larger system will give you a bigger jump. Why is not that the case here?
So I wonder if it's because this is much simpler in terms of the heterogeneity, and we sample enough of the statistic. Also experimentally, what Ramon did, he looked at different windows. So this was, I think, 200 millimeters, or I think 20 centimeters. So many tens of thousands of defects. And then he has the field of view with the camera, and then he looked at smaller and smaller windows, and he found that the results were very insensitive to the size of the window. So I think for this system, maybe the way that so in relatively, we saturate relatively small widths of the system. Whereas maybe in porous medium, I don't know, maybe you have these very mega pores, which are many connected pores, so you don't really sample easily enough. In one sample, you don't have a repetition of enough of these very small and very large pores. I'm not sure.
Did Ramon look at the velocity fluctuations of this front, or?
Sorry, again?
You have a, your front is really intermittent. I mean, it's a lot of, when you look at this burst activity, it's like almost like what we see in a fracture experiment that we are doing. And I'm just wondering if Ramon did look at the velocity fluctuations of this front. He could look at the PDF of the velocity fluctuation of the front.
Yeah. So
I think Ramon know well this work. So the fracture work that we have worked on before. So.
Yeah. So actually, this is something that I'm not doing myself yet, but Ramon and Jordi are doing with what's his name? Stefan Santucci. Yeah. So they are already doing some kind of experiment where they measure the velocities, and this will also, of course, clarify exactly the effect of viscosity for us. Yeah.
So what happens if you drive it faster? Have you tried to do that, because this is in the limit when you are driving it really slowly. Yeah. So I think you'll get a competition with the injection velocity and the fact that you have these jumps that maybe in some sense will put some cutoff of the Haines jumps that you have. Exactly.
I think at some stage, viscosity dominated, the viscous dissipation will dominate, and then the Haines jump will not be so important.
Okay.
Yeah.
Thanks.
More questions? Bjarne, I think, has one. Your mic is out, Bjarne.
Oh, I'm unmuting it.
Oh, now you go.
Oh, you heard me now? Okay, so I'd like to get back to the dynamics as well. So you're doing mostly quasistatic. So if you increase the frequency of the pressure drive, do you have any expectations what you'll see? I should expect one, you have viscosity getting in, but the other thing is that you have conservation laws, as opposed to most of my intuition here comes from ferromagnets, where you don't have a conserved order parameter. But here, essentially, the volumes are conserved.
Exactly, and actually, it will be very interesting, for example, to drive it at given velocity and not at given pressure jumps, which are, again, not exactly equivalent, because then if you have a constant saturation or you're fixing the saturation jumps, then because of the interface will want to jump ahead, but it will be restricted by the mass conservation. And then really the pressure saturation curve will be kind of more erratic, and it will be bounded by the pressure saturation curve at fixed pressure. And this is something that Ruben and Luis showed already in a paper a few years ago, 5 years ago, about hysteresis in pressure saturation. So the behavior will be different, as you said, because of this restriction by mass balance. The jumps will be limited by the fact that you didn't supply enough if the rate is not fast enough. Yeah.
All right. Do we have any more questions? I don't think so. So thank you very much, Ran, for joining us today. I see that you brought the Barcelona hub with you. I see Jordi and MD is probably Marco Dents in the audience. So thanks for coming, and hope to see you soon. Hopefully in some physical meeting when we can do that again.
Yes.
Okay.
Thank you so much.
Thank you. Bye-bye.
Thank you.
Bye-bye.